Welcome back to Geometry. We are ready to begin Chapter 5, and we will begin with perpendicular and angle bisectors. Try the warm-up, come back and check your work. Okay, so you probably did this just by sketching it rather than actually constructing it. A perpendicular bisector looks something like this, where we have a segment that is being split into two congruent halves, right, by another segment or line. Okay, an angle bisector is an angle that is being split into two congruent adjacent angles by a ray or other segment or line, right? And finding the midpoint, remember finding the midpoint, we just find the average, right? So we have -1, 7, and the slope is rise over run, so 1/3. The objectives today include proving and applying theorems about perpendicular bisectors and proving and applying theorems about angle bisectors. So let's think about this. When a point is the same distance from two or more objects, the point is said to be the same distance from the objects, right? Another word for same distance is equidistant from the objects. Triangle congruence theorems can be used to prove theorems about equidistant points. Distance and perpendicular bisectors. A perpendicular bisector theorem. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So point X here is equidistant from the endpoints A and B because line L is a bisector. We know that due to these little symbols that tell us that AY is congruent to YB, right? So X is on this perpendicular bisector equidistant from the endpoints A and B. The converse of the perpendicular bisector says if a point is equidistant from the endpoints of a segment, then we can now say that line L is a perpendicular bisector of the segment. Okay? Okay, so we are going to learn a new word today. It is a set of points that satisfies a given condition. A set of points that satisfies a given condition is called a locus. So the perpendicular bisector of a segment can be defined as all of the set of points, the locus of points in a plane that are equidistant from the endpoints of the segment. We are to find the given measure, mn. What is the length of mn? Well, mn is a segment that is created by taking the endpoint of ml, right, and going to a point n out here on this line. Notice this line is a perpendicular bisector. We have a right angle here. So we can say that mn must be equal to nl, right? So, and that's because of our perpendicular bisector theorem. And because it is, if nl is 2.6, we can say mn is 2.6 by substitution. Find each measure. In this diagram, we're looking for tu, the length tu. And we can see, again, a perpendicular bisector given by this right angle, and these little hash marks that tell us TW is congruent to WV. So we know that U is equidistant from T and V, the endpoints of that segment. So we can see that 3x plus 9 equals 7x minus 17, right? So we can solve for x, as I did here. And to answer the question, how long is TU, what do we do with our x? Plug it in, right? Substitute. 6.5 times 3 plus 9, and we have 28.5. So the reasoning here follows these statements. We have a perpendicular bisector theorem, we substitute it, and then we have the subtraction property of equality, addition property of equality, division property of equality. Okay, go ahead and find the measure. Given that line L is the perpendicular bisector of segment DE, and EG is 14.6, find DG. Okay, so once we know that this is a perpendicular bisector, we know that DF equals FE, right? And we also know that GE equals DG, and so we can say that DG equals 14.6. Very good. Find the measure. Given that DE equals 20.8, DG equals 36.4, and EG equals 36.4. So we can say that because G is equidistant from these endpoints of DE, that line L is a perpendicular bisector, can't we? And so we can say then that DF equals FE. And they are each half of 20.8. Okay? And so in this case we're using the converse of the perpendicular bisector theorem. And so DE therefore equals 2 of EF. And we know that DE equals 20.8. So we simply divide by 2, and we have EF is 10.4. We have two additional theorems, the distance and angle bisectors. The angle bisector theorem says if a point is on the bisector of an angle, then it is equidistant from the sides of the angle. So from point C, if we take the shortest segment to each side, those segments would be perpendicular to those rays, okay? And AC would equal CB. The converse of the angle bisector theorem says if a point in the interior of an angle is equidistant from the sides of the angle, we can now say that PC is an angle bisector, right? So, and if it's an angle bisector, we can say that the two angles formed by the bisector are congruent. So APC is congruent to BPC. Make sure you pause and reflect on this and really think about it for a moment before you move forward. So based on these theorems, an angle bisector can be defined as the locus of all points in the interior of the angle that are, that's right, equidistant from the sides of the angle. Find the measure BC. So we are given that BC equals DC because we see here that AC is bisecting the large angle BAD, the angle BAD, right? And we can tell that by the given information that these two smaller angles are congruent. So that is by the angle bisector theorem. And because we are bisecting, the length BC should be equal to DC, and we know that DC equals 7.2, right? So BC equals 7.2 by substitution. Go ahead and pause the video and see if you can answer this question. Measure of angle EFH is what we're looking for, given that the measure of EFG is 50 degrees. So the largest angle here we see is 50 degrees, and we are to find EFH. So we know that EH equals GH, and segment EH is perpendicular to FE, And segment GH is perpendicular to ray F, or I'm sorry, they're not stating that quite yet. Oh yeah, they are. Here we go. GH is perpendicular to FG. So we see that FH bisects angle EFG by the converse of the angle bisector theorem. Okay? And therefore we can say that this large angle, angle EFG, right, is being split into two congruent angles. If the large angle is 50, I'm sure you know what those angles measures would be. And so we can use substitution, can't we? So the measure of EFH is half of the large measure of angle EFG. And so half of 50 degrees is 25 degrees. And there you go. Okay, can you find the measure of MKL? Go ahead, pause, come back and show your work. So since JM equals LM, KJ is perpendicular to JM, and KL is perpendicular to LM, we know that KM bisects the large angle JKL by the converse of the angle bisector theorem. So the measure of MKL equals the measure of JKM. These two angles must be congruent. That's our definition of an angle bisector, right? And so we actually have that expressions we can substitute, right? So we do. We substitute the expressions for those angles. And now what can we solve for? That's right, we can solve for the A, the one unknown. So let's collect our A's to one side, right, by subtracting 2A from both sides. And then we'll subtract 20 from both sides, right? And we have A equals 6. And so if we are going to find the measure of MKL, we substitute the value for A into that expression, right? So we will substitute 6, and as I'm sure you know, the measure of angle MKL is 38 degrees. Okay, in this case, we are given that YW, that ray, bisects angle XYZ. And we are given WZ equals 3.05, so find WX, and as you, I'm sure know, WX definitely must equal 3.05, right? We can start by stating that these two lengths must be equal, given the angle bisector theorem, so we can simply substitute, right? 3.05 for WZ, and by substitution we know that WX equals 3.05. Okay, to save a little time on the video, go ahead and try this, and then I will reveal the answer, and you can just pause the video and check that out. Okay, and yes, we have 126 degrees because we are actually finding the large angle here, measure of X, Y, Z, which would be double 63, 126. Good. Okay, let's try this real world scenario, and pause the video, read, and come on back. So the main point here is AD is congruent to CD, right? So D is equidistant from A and from C, which means that BD is, let me just say that B is equidistant from A and C, so B then is in the midpoint, is the midpoint of AC, and BD therefore is a bisector, isn't it? It is definitely a bisector. So that is what they say here. It's given that AD is congruent to CD, so D is on the perpendicular bisector of AC by the converse of the angle bisector theorem. So since B is the midpoint of AC, BD is the perpendicular bisector of AC. Actually, when we were reflecting on this last year, we thought that really this could also be the converse of the perpendicular bisector theorem, rather than the perpendicular angle bisector theorem. I think that probably it's an even better case to say that it's the converse of the perpendicular bisector theorem, right? The key sometimes is going the wrong direction, isn't it? Okay, we're to write an equation in point-slope form for the perpendicular bisector of the segment with endpoints at 6, -5, and 10, 1. So you see here the graph of these 2 points and a segment that has been created between those 2 endpoints. Okay, so the perpendicular bisector of this CD will be meeting CD at its midpoint. So the first step is to find the midpoint of this given segment, right? And do you recall how to find the midpoint? I'm sure you do. We got to find the average of the x's and the average of the y's, right? So that's what that looks like. We add the x values, divide by 2, add the y values. Go ahead and pause and come back with that midpoint. And you should have substituted the known values and found that the midpoint is at 8, -2. Good. So we have the midpoint. We now need to have create the bisector. If it's a perpendicular bisector, we know that the slope of the new segment will be what compared to the slope of the original? Remember? It will be, if it's perpendicular, it will be the negative reciprocal, right? So right now we're going to find the slope of the given segment, and go ahead and find that. Come on back. And you should have found 3/2, right? And we need to recall that the perpendicular slope is a negative reciprocal of a segment's slope, right? So we know that the new line will have a slope of -2/3. Okay, so we're ready to use point slope form to write an equation. And we know that this perpendicular bisector has a slope of -2/3, and it passes through that midpoint that we found. So we have a point and slope. Can you jot down point slope form? And y minus y1 equals m times x minus x1. And so now we simply substitute y minus -2, or y plus 2, equals -2/3 times x minus 8, substitution, right? And now we can just leave it in this form. Actually, they asked us to write the equation in point slope form, so we're done. If we wanted it in standard form or in slope intercept, we could transform this equation. At this point, we're done. Okay, and that's what it looks like when you graph it. All right, so go ahead and pause the video and come back and check your answers. Okay, the answers are in red. And try the second part of the lesson and come back and check your work. And you should have this equation in point slope form. And there you go. Good luck.